Hi there, Biochemistry 2 students. This is the week 1 lecture video for our Biochemistry 2 course in fall of 2024. To introduce those of you who weren't here for Biochem 1 last year to this format, my goal will be to post a something like 20-minute or so video each week to YouTube. I'll embed it in Bear's Lair so you can watch it there. It will summarize the lesson and material that we covered that week, the lessons and the material that we covered, and should serve as a good reference. You shouldn't treat this as like the only lesson that you get. But it'd be great follow-up to what we talked about in class to confirm your understanding, since I'll go kind of fast, right? And that also works because you can pause me, you can slow me down by setting the speed of the video at half, or you can speed me up if you want me to go more quickly, or you can jump around in the video to parts that you want to hear more about. So hopefully that's a functional setup for you all to be keeping up with course material and really reinforcing your understanding of it. Also, if you're ever absent, these are great ways to come and get the information that you need from classes that you missed. As follow-up to that, unless it all makes really good sense to you, you might consider checking in with me at student support. And of course, if seeing it in class and watching the video still isn't quite doing it for you, feel free to certainly look it up in other resources if that's helpful, or just to come see me at student support so I can clarify things for you. Okay, so this first week was really about the periodic table, which is really what our first whole unit is about, is thinking about the elements that make things up, and eventually we'll be considering how those elements bond together to make molecules, and what the properties of those molecules are as a result of the elements that they're made of and the ways that they bond together. And we'll be culminating in looking at like some building materials, that the buildings that are currently in process of being refurbished that our school is in are made from. So kind of a cool application of chemistry there. The most basic thing that you got to know about elements is that they are composed of subatomic particles called protons, neutrons, and electrons. Protons and neutrons approximately the same atomic mass contribution. So basically 1 unit of atomic mass per proton and basically 1 per neutron. Such that if you have, oxygen 16, which is an isotope of oxygen, it has 8 protons and 8 neutrons. That's what makes it oxygen 16. Of course, we would also know that the atomic number of oxygen is 8 because 8 protons are found in oxygen, and that is definitional. That is what makes oxygen oxygen. I'll remind you that protons are positively charged. So in a neutral atom of oxygen, there would also be 8 electrons. 2 are distributed on the first energy level, and the other 6 are on the second energy level. We started to look at how you can use the periodic table as well as this electron orbital filling order chart that's in the top right of this sheet that I printed and gave out to you all to practice. We saw how you can use those to track the filling order of the electrons. That's the main focus of this video, just like making sure that you feel comfortable with that. So let's use oxygen as an example for our first example, right? So it has 8 protons and 8 neutrons in its nucleus. That is what would make it O16, which is the most common isotope on the planet. Other interesting information, we got that from our presentation on oxygen, hearing about the origins of its name as an acid generator and so forth. At any rate, I'll leave that part blank here because my focus is then thinking about the 8 electrons that go into the first and then second energy level. And I'm just going to draw them without worrying about being a little bit sloppy, so I can go quickly here. 6 electrons in the second energy level. So I can draw those out. That's where the 8 electrons are. Remember, the first row of the table has 2 elements. That represents the 2 electrons that fill that first energy level. And then as the second energy level starts being filled, there's a possibility of 8 electrons going in there, which is why the table is 8 elements wide. Same with the third energy level, if we're ignoring the 3D, which doesn't fill until after the 4s orbitals. And you can see that in the flow chart on the top right. The next row, 18. The row below that, 18. And then we start to get the F block added in. And so we start to expand even more to 32 wide rows. actually articulating the places these electrons are located, we should talk not only about energy level, which is the first number in an electron configuration, but also the specific orbitals that those electrons are going into. So for example, for oxygen, the first energy level only has one orbital called the s orbital, and the first two electrons go in there on that first shell. Then the second shell, the second energy level, has an s orbital that fills with the next two. And then it has p orbitals that could fill with up to 6. And you can see that on the flow chart here, number 6 there. But oxygen only has 8 total. So its configuration is 1s2, 2s2, 2p4. And unsurprisingly, we find it in what we could call the p block of the table in the 4th position of that block. So the p block, 4th position, would have a configuration 2p4. And we started to see, as we heard people presenting, that as you go down the column here, other elements in oxygen's column, which is called its group, have the same outermost electron configuration in terms of the orbital. In other words, oxygen ends with 2p4, sulfur ends with 3p4, selenium ends with 4p4, and so on. And what this means is, like, we're very familiar, I hope, with this molecule by now, H2O. That's water. If you have hydrogen bonding with sulfur, you make H2S, hydrogen sulfide, a sort of stinky smelling gas. Unsurprisingly, the bonding that those two do is quite similar, though their properties differ in some ways because of the actual elements that are there. So it's kind of worth noting that. One really big difference, just to point out to you, is if we looked at electronegativity. So let's practice that really quickly, because we also looked at how hydrogen with an electronegativity of 2.1, when it shares electrons with oxygen with a Pauling electronegativity value of 3.5, that means oxygen is much more electronegative. It pulls on the electrons much more, because the difference of 1.4 is enough to make the electrons be shared unevenly. That results in a polar covalent bond. Polar covalent bond. However, hydrogen sulfide, if you notice, sulfur having more electrons around its nucleus to shield the protons from a bonding pair of electrons, as you go down the column, electronegativity decreases. Sulfur, only at 2.5, is the same amount different from hydrogen that carbon is. So this is a nonpolar covalent bond, just like you would find in a hydrocarbon like oil or natural gas or whatever. The difference is only 0.4 in the electronegativity values of the two atoms involved in the bond. So there's no uneven sharing. There's no partial negative, partial positive character that you'd get in water. So unsurprisingly, there's some ways in which the molecules are different, but other ways in which, if you look at their overall shape and how many bonds they're making, we find similarities if we're matching up the same types of elements from in terms of like the same group, coming from the same group. Okay. We'll practice just one more in this video, just to make it a little bit like more complex of an electron configuration. So let's, for example, look at rubidium, Rb. Rubidium, I can use the table and say, well, it's got 1s2, it's got 2s2, 2p6. That gets me up to 10. I'm now at neon. 3s2. I'm now at magnesium. 3p6. I'm now at argon. 4s2, that gets me to calcium. Now the D block of the table. 3d10 fills next. And you can follow this in the filling order up here as well. We're here, 3d10. Then 4p6 gets us up to krypton's configuration. At any point, you can stop and count up the electrons, and it should match the atomic number of, since we're on krypton right now, it should match krypton. Krypton is 36, so 2, 4, 10, 12, 18, 20, 30, 36. Indeed, it matches. And rubidium is atomic number 37. So in a neutral atom, in a neutral atom, it would have just one more electron than krypton, and it would be in the 5s position. Remember, that also means we could just write rubidium as krypton with an added electron in the 5s1. And notice something else, that just like hydrogen has 1s1, lithium 2s1, sodium 3s1, potassium 4s1, rubidium would have similar characteristics in many regards to the other elements in its column, because its configuration's outermost electrons are in an s1 orbital. They're in the s orbital, and there's only one of them. So hopefully that's some pretty good practice. If you keep going with the flow chart, you might eventually get up to the 4F or the 5F. And again, that's what gets you down into the lanthanides and the actinides. And that's something that, comes up when you study electron configurations, but they're pretty complicated, those F orbitals. So most of the bonding that you end up looking at involves S orbitals and P orbitals, which is cool and useful, and luckily a little more straightforward than thinking about F orbitals and D orbitals. So that's the introductory material. Mix that together with the research that you all did on the periodic table on 2 or 3 elements each. In some cases, a few of you went above that. Nicely done. But learning those elements hopefully gave some character to some parts of the table, some interesting fun facts for you to be thinking about the properties of different elements and what people look for when we use them. And then also just understanding their electron configuration, their electronegativity, and their mass and proton content. A lot to have covered in like 3 class periods or what have you. So, on we go to building molecules next. Make sure that you feel reasonably comfortable with this, so that as we go on to building molecules, you'll be able to feel comfortable with why molecules have the particular atoms in them bonding in the particular ways that they do. Thanks, everyone. Hope the video is useful, and I'll see you all in class.